So here's something you probably already know. It turns out that most of the electrostatic attraction that happens in biological systems or chemical systems are actually the result of dipoles, little dipole moments that happen inside of molecules that then allow those molecules to electrostatically bind together. One of the greatest examples of this is water. The reason why water has that surface tension is because there are these dipoles in the water, and they arrange themselves so that the negative side of the dipole attracts the positive side of the dipole and vice versa, and you have this gentle little electric attraction that holds the surface together all nicely. And so it seems important then to figure out how we might be able to calculate those electric fields due to a dipole. So that's why we're here. That's what we're going to be doing. Let's do it. Let's imagine that we have two axes right here, okay? An x and a y axis. And upon those axes, I have a positive charge and I have a negative charge. Thus, I have a dipole, okay? A dipole is any time that you have positive and negative charges separated, okay? Now, in a molecule, these dipoles can simply happen because you have different atoms that are more or less electronegative, right? So for the classic example is an H2O, right? So if I have an H, right, and two O's here, we know oxygen is more electronegative, hydrogen is more electropositive, and so you will have a dipole that, stretches from this positive hydrogen to the negative oxygen, okay? So that's how it works. It's not always specifically two charges or two ions separated. Sometimes it's just the arrangement in a molecule where one side is more electronegative than the other. Okay, so how do we calculate what the electric field will be out here or out here as a result of this dipole moment? Well, it turns out that if we want to find the electric field on the axis of the two charges, right? So on the axis of the dipole moment, then the electric field is going to be, as you can see on the slide over here, 1 over 4 pi epsilon 2 times this vector p, which is the dipole moment. So p is equal to the dipole moment. Okay. So, and that's over r cubed instead of r squared. Okay. So that means the farther you get away from a dipole, the electric field diminishes much faster because of this 3 instead of a 2. Okay. The bigger this number is, the faster the electric field diminishes as you move away, which makes sense because the farther you get away from a plus and a negative, they kind of start looking like they just overlap with each other. And if they just overlap, it's kind of like they're canceling out, right? So the effects of dipoles are much stronger the closer you are to a dipole. All right. Once again, folks, this 1 over 4 pi epsilon 0 we replace with a k, so 2k times the dipole moment over r cubed. And now we have a formula that we can use to calculate the electric field due to a dipole at some distance away from the dipole. Okay? And once again, this is on the axis of the dipole. But it turns out this changes slightly if we want to calculate the electric field over here. One thing really quick, what direction will this electric field be pointing? Well, we know that it'll be pointing away from this positive charge and towards the negative charge, but this positive charge is closer, so it'll be actually pointing up. Okay? The electric field will be pointing up there. And, okay, what will be the direction of the electric field over here? It's some distance that's on the bisecting plane. We call this the bisecting plane of the dipole. Well, in this case, E is just going to be equal to Kp over r cubed. So there's no 2 anymore, okay? So in this bisecting plane, it turns out that the electric field is a little bit weaker, okay? And what direction would that electric field be pointing? Well, it would be pointing you'd have two components, right? This component that happens because of the positive charge is pointing away in this direction, right? And then you have this other component that's pointing towards the negative charge. So if we vectorially add those, we're going to get something that points down. So the electric field here would be pointing down, whereas the electric field here would be pointing away, okay? So I just want to do one classic example, right? The most famous dipole of all, water. And so how would we find the electric field strength, if you guys could go to the slide that says E field of a water dipole? How could we find the electric field strength 1 nanometer from a water molecule at a point on the dipole's axis? So it's going to be on this axis again, right? So we're going to use this formula, okay? So in other words, we're basically trying to find the electric field at some point here, if this is our water molecule, a distance of 10 to the minus 9 meters away. All right. Well, you know, I hate to say it, folks, but it's just a plug and chugger, okay? Which means we just want to say, so the E of H2O on axis, we want to use this formula, is going to be 2 times 9 times 10 to the minus 9 times the dipole moment, okay? So there's two ways to find the dipole moment. A lot of times they'll just give it to you, right? In this case, they give it to us. It is 6.2 times 10 to the minus 30, okay, coulombs per meter, all over the distance, which is r cubed, so that's going to be 10 to the minus 9 to the third power, okay? Incidentally, the other way to find the dipole moment is always equal to the charge on each of these. If these are protons and electron, that'll be 1.6 times 10 to the minus 19, or it's whatever the charge happens to be, times the distance between them, right? The space between these. So you can always find the dipole moment by multiplying the charge of the two dipoles times the distance between them. But once again, many problems will just give it to you. It is something experimentally known for water that the dipole moment is 6.2 times 10 to the minus 30. Okay, if I put that in my calculator, I multiply it all together, I get an answer of 1.1 times 10 to the 8 newtons per coulomb. That's big. That's really big. Why would it be so big? It's because you're so close to the water molecule. 10 to the minus 9 meters, you're very, very close to it. This is why we actually have, you know, bugs able to walk on the surface of water. That's why little water droplets actually hold their shape, because you have this strong electric field actually binding those molecules together at the surface. One of the things that I absolutely love about physics is the fact that through physics, so many of the things that you learned about in biology or chemistry have a reason, right? All the but whys, we now can say, well, we know this because there's an electric field due to dipoles, and we know that charges in electric fields are attracted to each other, hence surface tension and hydrogen bonding.